Thanks a lot. And thanks for the invitation here. And I feel a bit old when I see all these people in the audience, but it's okay. So I'm coming from the east part of France, Nancy, northeast, like you are south. And just one commercial slide, especially because there is a lot of students I get. So Nancy is a very nice place, especially Loria, where you can make a lot of research on computer security. I just list a few keywords there. And with the most beautiful place, square in Europe, Place Stanislas, if you want to drink a beer there, I will welcome you. So, what is the menu today after this very nice lunch at noon? First of all, I will talk about what kind of issues are we talking about during this talk. And then I'll talk about disassembly of binary code. Of course, not regular binary code which come from GCC or the C compilers that you prefer, but which comes from malware writers. And then I will briefly discuss about this software that we call now Gorilla in English, which allows to analyze binary codes and find similarities, identify functions, and we'll see at the end if it works a short demo. So the first part of the talk is about what are the questions that we are trying to solve here. So there are at least three questions that we're interested in. The first one is how to identify a function inside a binary code. Why are we interested by that? As you know, it's not so easy, but if you know some malware or some virus, then you can build some signature and then you can identify it by looking at the signature. Okay. But this means that you already know the threat. If not, that means that you are downloading some binary code and you ask yourself whether or not it is a malware. In this case, the only way to deal with this problem, with this issue, is to look at the functionalities inside the binary code. For example, on your smartphone, you download some application with it's a game with a bird and whatever you want, and this application asks you, or does not ask you about looking to your position, your GPS position, to your contacts, and so on and so on. Is this a friendly game or not? The answer is up to you. But in some sense, it would be nice to detect in an automatic way what is inside, what is the functionality hidden inside a binary code. That's why we are trying to do that. So, for example, to some geolocalization functions or to some cryptographic function or whatever you want. And this is a kind of a preview of the results that I will show you later on. So, for example, with Gorille, we are able to locate that. This is a quite old example that WellDAC, which is a botnet, contains some cryptographic functions using OpenSSL somewhere in its code. So we are able to see that some OpenSSL functions are inside WellDAC, and we are able to synchronize both codes to see that on which address this correspondence can be found. The next issue that we are interested in is to classify. Classify, at first, this can be a bit weird. Why are we interested by classify viruses or malware? The problem here is that we have a lot of samples. For example, if you look at some numbers, like what Google people say about virus total, they receive something like 300,000 files per day, probably more. And so you have to say what are inside these files. So you have to be very quick. Even 1 second per file is too much because you have to analyze that very quickly. So this is kind of known as triage. I'm not sure it is an English word, but I think in French it makes sense. We have some success, as you will see, about that also. For example, we look at some regime loaders, and just by looking with our methods of morphological analysis, we are able to draw 3 clusters. And these 3 clusters are based on the API calls, and you see that's 2 different ways of building this loader for regime. Of course, the last issue is, in some sense, well known, is to detect, to know whether or not you are in presence of a malware or of a virus or a botnet. And it is maybe not so difficult when we already know the malware, but obviously when it is an unknown threat, it's difficult. And what I'm going to show you is that you have some new ways to detect malware using some database of signature, which are based on something else, based on the control flow graph of the of malware, and using some signature of white software, white application, white library, which are not forbidden to be run on the system. So, as you see, I am a professor at a university, so I always like some theoretical part of this aspect. And since I have a lot of young people here, young compared to me, recall that all these problems are completely indecidable, thanks to Kurt Gödel and maybe some other guy. And you see that to detect this border between the goodware and the malware, this is indecidable. That means that you don't have any programs which are able to exactly each time say that it's a malware or a goodware. In fact, it is worse. Oops, sorry. It is worse thanks to not to Turing, but to someone called Rice, that even identify functions inside a binary code. This is also indecidable. So we are in very difficult trouble, but nevertheless, we are trying to solve partially this problem. So this is only 2 slides of theoretical aspects, that's all. So why it is difficult? It is difficult because, in fact, you are there in this big room. When you are looking at some malware code, and we have plenty of very good talks this morning about that, when just you open some binary with IDA and you look at the code, and sometimes you cannot understand anything, or you have to drink a lot of coffee and to spend all the night to try to understand what is going on. There is some very nice books, this one and some other, about how to transform a very nice code into something very messy. Among difficulties, there is of course all these obfuscations, and we have some examples this morning. All the cryptographic functions that are inside the code to hide some informations. And also these 3 last items, which are self-modification. I'm going to talk a lot about that. Code overlapping, which is not too difficult, but still you have to be very careful. For example, if you look at disassembler, a well-known disassembler like IDA, and if you look at some code overlapping, in this case, IDA is not able to deal with that. And the last point is also very tricky. It is about all these tricks to avoid dynamic analysis when you are running a malware inside a sandbox, and the code is just aware of that it is monitoring, and so you will just evade in some way or another. So how to deal with all these protections against analysis of code? So for this, we are going to jump to the second part of the talk, which is about the disassembly of binary code. So I'm just focusing here in this talk because I have only 45 minutes, so it's quite short to say everything about binary code which are self-modifying and with instruction overlapping. That's all. So first of all, we are going to define what is self-modifying code, which is kind of very, I think, one of the most difficult protections to remove nowadays. When you look at some malware, at first, there is an entry point, so you can run it from this entry point, and then you have a first wave of code. And usually, this wave of code behaves like a packer or something which will decrypt another wave of code. So there can usually a loop, and I think this morning we also see this kind of loop. You have a loop which decrypts some data, and then you jump to some decrypted data, which is another wave of code. And of course, well, there is another wave, another one, till a final wave, and the payload of the malware or the payload of the program is somewhere between the first wave and the last wave, between the wave 1 and 18 in this example. This example is a concrete example which comes from the packer named TE-log that you can download on the web. And so you can see not all, but we'll see most of the malware as a sequence of waves. So if you just look at the first wave in a static analysis, you see nothing. You see just the first part of a packer, which we're going to unpack something, but that's all. And this is a typical schema of a self-modifying program that you are facing currently. Of course, if I go from the good side to the bad side, it's very easy to develop some self-modifying programs that are much more tricky than the ones that we are analyzing now. So just to be clear, here's a very short portion of assembly code. You see that there is a XOR on the middle of a loop. So this loop will decrypt some data somewhere, and then you jump to the part that you just decrypted. That means that if you look at the program at first like that, without running it, you just see this decoding loop, but not the next part. So one way to look at the second wave is to run the program in order to see what is inside the second wave. So exactly what we are going to do, that means that at first we have some payload installer, which will develop or which will deploy several waves. And then at some point there is a jump, and then the payload is running. That means the real program is there. Just to be a bit more precise about what I'm calling waves. A wave, you see, you can begin with just a run of the binary code that you are analyzing. How to do that? You take your program, your binary code, you put it in some virtual machine, some sandbox, you run it, and you try to capture each instructions with all the value of the registers and so on. And you look at them as the traces. So each node of this trace is an instruction plus some information on the stacks and the registers and so on and so on. So, and you will see that at some point, there is some instruction at the beginning on the blue part, which will write something on the red part. And then at some point in the future, again, there is a write on the red, and so on. And you will advance, and at some time, there is a node on red, which will be run. That means that at some address in memory, this address has been written and then run. In this case, this is a witness of the fact that you are going to change from one wave to another one. So with this very simple mathematical definition, we are able to compute these waves very easily just by looking at the fact that you have in memory one written instruction which wrote some bytes in memory, and then these bytes are run. Okay. So this is a very nice way of protecting a malware, of protecting some programs. Not only malware are using this kind of protections, a lot of legal programs are using also this kind of protections. So the very first question that we asked in my lab was, is this really a protection or not? So we ran some a project that we call Wave Atlas, just to see if all malware, or most of them, or how malware were protected. So for this, there is 2 labs, one in Montreal and one in Nancy. And so we have this kind of architecture with some, a lot of virtual machines running in some safe environment. And we run some binary code for some times. Then we look at the traces and we try to see if whether or not they are self-modifying in the sense that I just giving to you. And the result was the following one. For this, we use very known malware families that you can read the name on the top of the slide. So you see the results here, and what we see is that there is only a few which has only one wave, but these are not self-modifying, just a few moments. When you are writing a program, it's always non-self-modifying. Okay, you start with your C functions or whatever in Python, Ruby or whatever. You have only one wave. You are never writing some modifying codes. I guess so. I'm not able to do that like that. If I want to protect some program, I will use a packer. But by itself, developing a self-modifying code is quite tricky. I'm too old. Okay. But what you see is that most of them using 2, 3, 4, 5 waves of protections. That means, for example, that we can, and there is also some other results saying that the payload, that means the real meaning of the program, is at the last wave or the one before the last wave, on the 2 last waves. So all the payload is there. So with these results, the next step is to design and to develop some disassembler which is able to deal with these self-modifying programs. And this is part of the thesis of Aurélien Thierry, which is there somewhere, I don't know where. Aurélien. So co-design the disassembler, which is based on this wave model that I just showed you. And the good point is that waves are easy to compute, as soon as you have some traces. And the key idea is that each wave defines some non-self-modifying programs. So in each wave you can use some static analysis or some traditional analysis, that the one that you want. So in order to compute a trace, you are running some dynamic analysis, and for that you are using virtual machines, VMware, VirtualBox, several virtual machines. And we use 2 tools. One, to trace a program, we use either PIN, developed by Intel, or Dynamo Rio. And if I succeed, I will make a demo with Dynamo Rio, which is the new tracer that you are using since this month. So the main idea is the following one. So we have some secure sandboxing. We run the tracer either with PIN or Dynamo Rio. We collect some execution trace from the first instruction to the last instruction. And then we cut it wave by wave with this definition of waves that I just gave you. Then from each wave we extract the memory dump in order to look at what is inside the wave. Why are we interested not only by a trace, by the memory dump? The reason is quite easy, because a trace is just a trace, just one execution. And the execution depends on the input, on the system, on the configuration of the system, on the date, on the ways, on the, where is your mouse, on the what you have in your trash of your computer, and so on your desktop, and so on. So you have to look you have to take a trace like a kind of witness, but you have to consider what is not seen. That means, but you can download it using this memory dump system. Then we have, for example, if we see that there are 18 waves, in this case, we are going to take 18 snapshots of the memory just to disassemble all these 18 snapshots. Of course, this is the easy case when there is 18 waves. For example, Armadillo using, at least this version, uses 2 threads and something like 164 waves, which is a lot to follow. And usually the system is very difficult. So Codesign is using that, and then we disassemble each wave. And another question which is quite also tricky is about the fact that at some point you can have some instruction overlappings. And here is an example. I don't remember, it's come from UPX, I think so. So you have the first instruction is not interesting. The second one is the jump. And you see the jump +1. So you jump on something on yourself. And if you look at, for example, this very small assembly code on IDEA, is not able to see that you are jumping on yourself, and so the next instruction is a decrement and not the one that you can compute after. So Codesign is able to see that and to take into account instruction overlapping, and to trace that. I'm just talking about the tracer, just a few words. We implement a lot of countermeasure to avoid evasion techniques used by malware writers. There are, of course, other difficulties, and I see that Robin is somewhere also there. You have a talk by Robin yesterday, I think, about this subject, so I will be very brief. Even if you have one trace and you look at the snapshot of the memory for each wave, there are still some difficulties. And the difficulties come from opaque predicates, comes from indirect jump, when you have something like jump EAX, where what are the values of this register. So if you don't know that, you don't know where the target of the jump are. Also, all the problem of when you see a return instruction, is the return instruction the one that you expected, or does stack is the stack modified by some other instructions? All that you have to solve that. And one way to do that is to use dynamic symbolic execution. And we have some very nice tools developed by Robin in his PhD thesis using the BinSec platform. And this is not yet integrated in Codesign, but I hope it will be very soon integrated. So the overall architecture is the following one of this disassembler. We take a binary code, we have this tracer, we just recover all the waves that we can find. We take the snapshots of memory for each wave, the trace that we cut piece by piece, wave by wave, and then we disassemble it, and we also have a plugin to indicate to IDEA how to disassemble correctly, especially when there is some instruction overlapping. Codesign is under revision in some sense, so you can still download the source code of the old version in my web page, but soon there will be another version, so maybe it's more interesting to wait a bit. With that, you are able to, to disassemble most of the packers with their payloads, which is quite, I think, a quite good success. And at least it shows that Codesign is able to make a good job when there is some software protection using self-modifying methods. So the last part is about morphological analysis and the software called Gorille, and how do we use the output of Codesign, of the disassembler, to identify functionalities and to identify malware. So where are we now? We have this disassembler. We are able to recover the control flow graph. So that means that we start with a sequence of bytes, then we disassemble, then we are able to recover this graph, which is called the control flow graph. And now with that, we are going we try to answer to these three first issues, which were to identify functions, to classify malware, and to detect malicious code. Very quickly, the basic idea, maybe the only idea to remember about morphological analysis is on this slide. The idea is that now a signature is a graph, and this graph is an abstraction of the control flow graph. It's not the control flow graph of a malware. This makes no sense. But it's just an abstraction, a kind of a part. And so if you agree with this definition, to detect a malware or to detect a functions, it's just to detect that there is a subgraph inside the graph of the program that you are analyzing. So in this case, if this part in white is a signature, and if you see this part, the subgraph somewhere, you can say that there is some similarities. And then you can check that these similarities correspond to the same functionalities. So, for example, take this very short assembly program. Then we compute the control flow graph. As usual, it's not difficult. In this case, it's not difficult. And then we abstract it. This is a very short abstraction. I just forgot that it is a sequence of instruction. We just say if it is a sequence of instruction like move, addition, incrementation, and so on, just say it is an instruction. And you just consider the conditional jump, a return, call, and that's all. And you have a kind of abstraction. This is a very simple, rough abstraction, but it's an abstraction of the control flow graph that you can use as a signature. So we have a very nice construction where you can see that at each point the reduction is made, and the color of each node of this graph corresponds to one of the abstractions that you can make in order to have a nice representation of this program. But of course, this is not sufficient. You have to push this idea of abstracting the control flow graph, and we are using some reduction. That means you have a graph, and we are reducing it by preserving, it's a big word, but by preserving the semantics, some semantics of the program. That means that if you are a good plumber, see plumber ring, if you can take this path, when you are reducing the graph, you can always take this path. Maybe it will be shorter. It doesn't matter. Okay? But if there is a path, the reduction should be able to conserve this path. Well. But it's not enough too. You have to, again, to work about this idea, because finding functions or identifying some malware, it's like a puzzle. And the signature that you build, as I try to explain you, is something like that. You have some nodes and you have some edges between nodes, and it's quite large. So it is like a puzzle, giant puzzle. And one very important point is to cut this very large control flow graph that you have, this very large abstraction of the control flow graph, into small pieces. Okay? And then you have a set of small pieces of your puzzle, which are small abstraction of control flow graph. And now finding some similarities or finding some functions or saying that some program is a malware is just to take these pieces of the puzzles and to put it in the program that we are analyzing, seeing the connection and so on. Of course, we will not be able to cover all the programs that we are analyzing, but just maybe some part. But this is sufficient, because if I say that the program that you are running every day on your computer is using 50% of Stuxnet, you can say there is something wrong. Okay? It's exactly this basic idea. So the architecture of the morphological analysis tool, which is named now Gorille, is the following one. It is, the beginning is very identical to Codisasm. That means that you have dynamic analysis. You recover all waves. Then you take the memory snapshot of each wave. From the memory snapshot, you construct the control flow graph, you reduce it, and you compare its abstraction with the database of known functionalities, bad functionalities, and you see if there is some matching between the program and the database. So this is quite traditional in some sense, this kind of approach. Here it's a bit more interesting because you can have security policies. That means you can have bad patterns, bad control flow graph, bad abstraction of control flow graph, and good ones. So ones that you are say, okay, this one is harmless, so I can say it's okay. And the one that you can say, no, this one it is forbidden on my computer. So just a summary of what I have said before the demonstration. So we have a model of self-modifying computation, which is based on waves, which is very completely necessary if you want to look at malware, because malware are always now running as a self-modifying programs using packers, at least using packers. We have this disassembler which is named codisasm to deal with self-modifying codes and with overlapping instructions. And we have a very nice tracer which is used anti-debugging tricks. And I think soon we'll have all this work on the dynamic symbolic execution to have a better results with the codisasm. And then, as the outputs of the disassembler, we use these morphological techniques by abstracting the control flow graph in order to identify either functions or to detect malware or to classify also malware. So, the demonstration, this is in French because if someone are interested by coming to Nancy, just send me an email or just talk to me during the break. So let's look at the first example. This is really running. You see there is an error at the beginning because the database does not exist. And this is a new version of the tool, so there are still some bugs and it's not perfect. I run the tool named SIGtool, just here, saying that I would like to learn, that means to construct this database of samples of the malware named Stuxnet. Okay, there's only a few here. There's 5 samples here, and each time, for example, if you look at the first one here, it may learn OK, the name of the sample, and now it indicates the number of sites. What is a site? It is one of these pieces of the puzzle. Okay? Remember, I have this abstraction of the control flow graph, and then I cut the puzzle into small pieces, and one piece is named a site. And so here, in this case of Stuxnet DLL, I have about 1,000 sites, and since the database is new, there is none are known. Then there is a number of nodes. You see there is something like 2,000 different nodes on the signature, and then there is a lot of details. We can transform this database into a SQL database and to ask some requests, but since I'm a bit running out of time, I just skip this part and going directly to the detection. So here I'm running this command to SIGtool with option D for detection. I use a database of the 5 Stuxnet samples, and I look at a program which is one version of Yuku. Okay, and as you know, because I'm sure you are reading that on the web, that there is some relationship between Stuxnet and Yuku, at least at the level of the code. There is some parts are completely the same, not completely the same, but quite the same, very similar. And what you see that in this case, oops. So in this case, Yuku there is about this number of sites, 2,000 sites, which are matching against the Stuxnet database. And you see that here there is about 500 sites which are matching with Stuxnet DLL and 2,000 sites which are matching with the another Stuxnet sample. So you see like that, we see that in automatic way there is a relationship between Yuku and Stuxnet. And the tool is able to see to you where to look at the similarities. At this address, there's a similar function, so you can look by with the idea where are the similarities and to check that it is not wrong. And usually it's perfect. You can have a JSON output of all these similarities with all the address and all the information that you need. For example, we can also output, I'm going to be a bit quicker. We can also, oops. We can also output the graph if you want to see, look at it, what is inside the database. So this means that the whole graph, this is the signature, the full signature, and we are going to cut part of the signature into small sites. Another part of the demonstration that I will skip unless you really need it. Here I'm using Codisasm as a disassembler in order to build the control flow graph. I can also use IDA and ask IDA with a small script, a Python script, to output its disassembly of some code, transform that in some special format, and then I can use that with SIGTool. Here's another example. I'm using now another known, very well-known malware, which is named Babar. This one is quite funny, at least because of his name. So you see quite surprised if you compare Babar with the database of Stuxnet samples, there are some match. You see there is 1,000 similar sites, and here 800 similar sites. And if you read this very nice review MISC, or you look at all the good websites, you see there is no relationship between Babar and Stuxnet and Yuku. So there is a problem here. Not at all. Here we are not detecting something specific to Yuku or Stuxnet and Babar. We are just detecting some standard library. So they are sharing some standard library. Of course, they are not redeveloping OpenSSL and so on. They are using that. So to have a very nice detection, you have to remove common library like C library and so on, Windows library. So for that, I'm going to learn some whitelist. It's a bit long because PDF DLL is it's a large file. Then I can learn Stuxnet, but using the fact that I'm removing some white sites. So now I'm relearning Stuxnet samples reconstructing a database, but I'm removing all the white sites. Now we can check that Babar is not detected. And you see that I'm running the seek tool to check if Babar is detected. And here it is written 0 unique matching sites, saying that Babar is not anymore detected if you just look at Stuxnet samples. Just a very quick, I have other demonstration if you want, but maybe just to see, so for the, just a very quick demonstration of the dynamic analysis. So in this case, I'm running here on VMware, just some very gentle example. So I'm running on, for example, just for the example, the program that you know that is hostname. And so the tool is just tracing an execution of hostname. And you see at the end that it tells you that there is not 2 waves, there is a bug here. There's only 1 wave, and it outputs the wave, the first wave, the only wave. Now, I'm not sure you are completely seeing that. Okay. If you see on the top here, it is the same hostname program, but which is packed using UPX. Okay. I'm going to run that using the tracer, which is based on Dynamo Rio. And you will see that at the end, if it works, at the end, there is 2 waves. You have this number 3 minus 1, which is 2. And on the 2 waves, there's wave 0 and wave 1. And it is able to download both waves, so we can use that to make some morphological analysis on it. So, for example, we can look at the simple example where there is just hostname, which is trace. And in this case, we can ask what is inside. And we see that there's only 1 wave. We can learn from the memory snapshot, we can learn the program hostname. And then we can compare the program hostname that we just traced against the version of hostname which is packed with UPX, and you are going to detect that the packed version of hostname with UPX is hostname. And you see here is so it is I just compute the distance between UPX hostname with the database containing just hostname, and you have something like 100 matches. That means all sites are matching. Maybe more interesting. More interesting, instead of looking at all waves, I can look at each wave and determine on which wave hostname is hidden. And in fact, here it's UPX, there's only 2 waves, so it is hidden on the last wave, which is the wave 1. I'm just extracting this wave, only the wave 1 is extracted. And then I'm just detecting in this last command the fact that hostname is on the last wave of the packed hostname with UPX. So I'm saying I'm running out of time. Yes, it is a demonstration. It's always too long. If you have any questions, please ask. I have a very nice movie of my lab, Gloria. So I'm just putting this movie so you can look at that.